So taking a look at this, what I really want us to, come away with is understanding that if we're looking in quadrant 1, 2, 3, and 4, so that's what we're describing as S increases from 0 to pi over 2. That's in quadrant 1. What's happening with sine? What's happening with cosine? From pi over 2 to pi. What's happening with sine? What's happening with cosine? So let's watch. As it comes around the unit circle here, we can see that the sine value increases. Right now it's at 0, all right? And then we're watching our triangle height get larger and larger and larger. And then the purple piece, the cosine, is getting smaller and smaller and smaller in quadrant 1. So sine is increasing and cosine is decreasing. All right, let's go back to watching the circle. What's happening in the second quadrant? Sine's getting smaller and cosine's getting bigger, but in the negative direction. Okay, so we're going to say that it is decreasing. So sine is decreasing from pi over 2 to pi, and cosine is decreasing from 0 to pi. So you can observe what's really going on in each different quadrant here, all right, to really understand when sine goes from increasing to decreasing, when cosine goes from increasing to decreasing. And you can see it on the graphs on the right. All right, sine reaches a maximum at 1 right now, all right, and then decreases to 0 slowly, all right, but then when sine is at 0, okay, cosine's at its lowest possible point, and there's a point where they do equal each other, all right, and then we can see that sine dips all the way to -1 while cosine's hitting 0, and then back to the pattern. All right, so hopefully that helps give you a good visualization of what's going on, and you can actually, see the unit circle and how it produces a sine or a cosine wave. So this one is literally just showing all of the sine values of the function as it goes around the unit circle. So this one's strictly showing sine. Notice we start at 0. It has a maximum at pi over 2 or 90 degrees, and then it goes at 180. It sine's back at 0. All right, and then back up. So there's a nice little sketch. So hopefully you understand, when we talk about the sine function, how it's created, and then it just repeats itself over and over and over and over. Generally, though, we graph sine over the course of 2 periods. So we can see 2 periods here is from -2 pi to 2 pi. 1 period here is from 0 to 2 pi. Another period is -2 pi to 0. So we can just take a look at that. Each chunk, when it completes one pattern, that's 1 period. So it's very important for us to understand the domain and range of sine. Sine goes from -infinity to +infinity. All right, it goes on forever, and its range goes from -1, that's the lowest it's going to get, all the way up to +1. You can graph this on your calculator. You can hit y equals, you type in sine x, close parentheses, and you hit zoom 7. Zoom 7 puts it in a nice trig layout when you do that, and you can actually see the trig function. You should recognize the table on the left, okay? Those are our special triangles. Pi over 6, right? So we got 30 degrees. Pi over 4 is 45. Pi over 3, okay, it's 60 degrees. Pi over 2 is 90. Those are all the very, very important angles that we know as we go around the unit circle. So notice a basic sine function, all right? The range for us, our answers need to be between -1 and 1, and it's in brackets, so we do include the value. All right, so this is just a brief synopsis of what I just kind of talked about. All right, the basic period for sine is 2 pi. You do need to know that. Here's what we need to know though. Sine is an odd function. It's symmetric about the origins, so you can fold it over the x-axis, then over the y-axis for it to be on top of itself. So in this domain, if we have sine of like -pi, okay, sine of -pi would be what? 0. So is sine of pi in the negative in front. So since it's an odd function, sine of -x equals negative sine of x. Okay, it'll just be, if the opposite's in the argument, it'll be negative on the outside of the trig function. Okay, let's take a look, just cosine now. Notice cosine starts at 1, right? Because cosine of 0 is 1. We have like an absolute maximum horizontal distance, and we don't have a vertical distance. Now this graph's a little different because it goes back and forth, and it rotates counterclockwise, then clockwise. But this is generally how you're going around the unit circle and how you actually create the model for a cosine graph. Cosine is very similar to sine. The cosine still has a period from 0 to 2 pi, so you can see that. And cosine starts at 1, so notice on the y-axis, the cosine value is at 1. The domain is the same as sine, negative infinity to positive infinity, and they also have the same range. The range on cosine is from negative 1 to 1. You can also graph this one in your calculator. All right, you go into open your calculator up, hit y equals, type in cosine x, close parentheses, hit zoom 7, and you should be able to graph exactly what you see on the screen right there. And just like with the sine values, okay, the table on the left-hand side, all our important triangles and values that we've calculated as we've gone around the unit circle. And so cosine, just to reiterate, the x-intercepts, okay, where they come about is 2n plus 1 times pi over 2, where n can be any integer, right? So if it's 0, if n is 0, right, it crosses at pi over 2. Well, it crosses every time it turns 0. So it's at 0 at pi over 2 and 3 pi over 2, and for all those n's, okay? Same as pi, like we talked about, period. Cosine is an even function, so if we take cosine of like negative pi, all right, we'll actually get back cosine of x, okay, whatever cosine of pi is, okay? So that's really the answer to this, because it's 180 off. When you fold cosine, it's even because you can only fold it over the y-axis, and it lays on top of itself. So that's helpful to understand what it's even. All right, let's do some examples though, because I just told you, right, that sine had a range of negative 1 to 1, cosine had a range of 1 to 1. What we're going to do is we're going to change the range of sine and change the range of cosine. So our first example here, if we want to graph y equals a sine of x, where a is going to represent any number we want. In this example, we're going to graph a sine x. We're going to have a equal to 2. So we're going to change what we call the amplitude of sine. And we're going to compare it back to what I'm going to call the parent function. The parent function for this graph is y equals sine of x. Okay, so the function we're going to analyze is 2 sine of x, and we're going to compare it to the parent function y equals sine of x. We're going to see, hey, what exactly happened between the two graphs here? It changes the range, okay? The amplitude, the digit that's in front of the sine, changes the amplitude of the waveform. All right, so all we do is take all the sine values that we know and we multiply them by 2. It's a scalar, it's a multiple. Okay, so that's really what we're doing. We're going to change it. If you were to graph this in your calculator, this is what you would get out. All right, you would hit y equals, so on the first line you would have 2 sine x. On the second line you would just have, on y2 you would have sine x, and hit zoom 7, and you would be able to see. Notice what doesn't change about sine. What doesn't change is where it crosses 0, or crosses the x-axis. It crosses still at 0, still crosses at pi, and still crosses at 2 pi, right? Because remember, sine of pi is 0. 0 times 2 is 0. So we're not changing any of the intercepts. We're only changing the amplitude, or how high this wave can become. So that's what changing the a value in front of a sine or cosine function does, is it changes the amplitude of the wave, or the height of the wave. And this is a very important key term. You keep hearing me throwing it around, but this is really what it is. It says the amplitude of a periodic function is half the difference between the maximum and minimum values. It describes the height of the graph. I'm going to step back a slide, because what does it mean to be half the difference between the maximum and minimum values? If we step back, all right, and we're looking at the blue graph here, the maximum value is 2. That's as high as it gets. The minimum, all right, or the lowest it gets is negative 2. So we take half of that, which is no matter what, it's going to be 2. All right, so that's what the amplitude is as we take a look at that. And it does the same exact effect for sine or for cosine. So a general equation for us is y equals a sine x, or y equals a cosine x. Okay, that little a in front changes the height of the wave, what its maximum is going to be and what its minimum value is going to be as it oscillates. So no matter what the value of the amplitude is, the periods of y equals a sine x and y equals a cosine x, they're still 2 pi. And I showed you that on the graph where you could see that sine was still going to be 0 at 0, pi, and 2 pi. Alright, now what's going to happen if we do something like this now? Notice the 2 is in the argument. The 2 is in the argument. So what's really going to go on here when we do this? Alright, I really want to study this table, kind of see what happens as we go through. What happened, if you looked at this, is that only one complete circle occurs in pi units. We're changing the period now. Whereas before, sine, the period was 2 pi, 0 to 2 pi. Same with cosine. But now that the 2 is in the argument being what happens after sine, what we normally put in parentheses, since it's sine of 2x, what's happening is what? That's happening twice as fast. It's happening twice as fast now. So that signal is going to be twice as fast. So now sine has a period where it repeats every pi. So instead of one complete period in 2 pi, it's going to happen twice in 2 pi. Okay? Now, this is a graph I just wanted to show you again for understanding the amplitudes. Alright, we can see what the different amplitude is. Whether we put a 2 in front of sine x, what happens to it, how high and how low the wave gets. Alright, when we compare to the parent function that's in red. And then, alright, in blue, that's half sine. So if we put a fraction, okay, in front of it. But notice that it's sine of 0 is still 0. Sine of pi is 0. Sine of 2 pi is 0. That part isn't changing, okay? Let's talk about what's going to happen with sine y equals sine of 4x now. Exactly probably what you thought would happen with y equals sine of 2x, only now it's going to happen what? Notice it's going to happen 4 times as fast. So from 0 to 2 pi, it's going to happen 4 times. This table is only showing 0 to pi. So we've split it up now. This is happening twice as fast as the other one. So it's happening twice now from 0 to pi. Alright, when we've done this. So we can say, you know, what's the period and how do we calculate the period? The period is 2 pi over b, where b is the number in the argument. So in our scenario here, b is 4. So we would take 2 pi over 4 and reduce that down. Alright, 2 pi over 4 reduces to pi over 2. That tells us the period. If you look at this table, the first wavelength goes from 0 to pi over 2. So make sure you listen to this part in the video a couple times and write down what I said. The b is 4. And to find the period, you take 2 pi over b. So 2 pi over 4. 2 pi over 4 reduces to pi over 2. So if you look at that, 0 to pi over 2, alright, that's 1 period when we graph this. So very, very important stuff. When we have a magnifier inside the argument, alright, it's going to make the period go faster and faster and faster. So a few minutes ago when I was saying, alright, here's the b, alright, this is the part I'm looking at. We have y equals sine bx, or y equals cosine of bx, any value that's there. So to find the period, you have to take 2 pi divided by b to get the period of that function. Okay? Then we're going to actually graph these now. Alright, so we're going to divide that interval into 0 to 2 pi into 4 equal parts. Okay, so we're going to divide that into 4 equal parts when we do this. Then we want to find the values where those parts are equal to -1, 0, or 1. Those are going to give us the maximum points, the minimum points, and the x-intercepts on our graphs. Okay, so we want to find the midpoint of the interval by adding the x values of the endpoints and dividing by 2. That's the same way we find any midpoint, right? We add 2 things together and then divide by 2. That's going to be the middle for us. Okay, so it's important for us when we want to do the graphical approach on this. Alright, so let's take a look at this graph we've already looked at. We want to graph y equals sine of 2x. We've talked about this one already. We're going to compare it to the parent function of y equals sine of x. Okay, so what we need to know is the coefficient is 2. That's our b, so b is 2. We calculated this before. The period is 2 pi over b, 2 pi over 2, because b is 2 in this case. 2 over 2 reduces to 1. So the period, we're going to have, the graph will complete one period over the interval 0 to pi. And we already kind of talked about that looking at the table. So now we have to find the endpoints. Okay, so we have to know how to calculate these. This part is extremely important. Okay, if we know the endpoints are 0 and pi, we have to find the 3 points between them. Okay, the easiest one's to find the middle point. Right? We take 0 plus pi and divide it by 2. In this case, it's 0 plus pi. We're multiplying by a half. Same as dividing by 2. That's going to be the middle point. Okay? And then we have to find the other middle point, the middle point between 0 and pi over 2. Well, we can either take that and divide it by 2, or we know that we're going to take it into quarters. So we can find what's a quarter of 0 to pi, so 0 plus pi times a quarter, or we can take 0 plus pi times 3/4 to get the other points. Okay, we know our left and right endpoint are 0 and pi, but what we're calculating here is going to tell us the next part of sine, when its maximum occurs, when it crosses the x-axis again, and when its minimum occurs. 3 very important parts for us to determine the graph of this function. All right, and what's really going on. So we're going to break it down into this. We have the left and right endpoint, and when we did the math, the first quarter was pi over 4, and the third quarter is 3 pi over 4, and we found the midpoint to be pi over 2. We're using the example of y equals sine of x, right? We're going to graph that. We're going to compare what's happening when we compare it to the parent function of y equals sine of x. So now when I put them on, and I want you to really make sure that you pay attention. These values we just calculated in these couple slides right here. So down at the bottom, this is very important. All right, these values, if we look at the graph, they're showing up on our graph here. What's in blue? So remember, the blue graph is y equals sine of 2x, and the dashed line, or the pink color, that's y equals sine of x, the parent function. And the blue is y equals sine of 2x. All right. If we take a look at this, we graph this and we mark the values that we just calculated and came up with on the graph so that we're able to graph y equals sine of 2x. Now if we compare the two, notice one period of y equals sine of 2x goes from 0 to pi. That's how long it takes it to repeat itself. Notice the parent function y equals sine of x, it goes from 0 to 2 pi to repeat itself. So you can see what we've done is we've cut the period in half using that 2 as a multiplier. Okay, in the argument, so y equals 2 sine, or sine of 2x. All right, so just to recap here, if we're going to graph and find the period, b has to be bigger than 0, right? Because if it's not, we have division by 0 and it can't work. But if we have the graph of y equals sine of bx, it's going to resemble that of y equals sine of x, but we're going to have a different period. And the way you always calculate this period is 2 pi over b. B is always going to be next to the x variable in the argument of the trig function. The argument of the trig function, as we see here, is the bx. Normally, it'll be in parentheses for you. The same exact thing works for cosine. Okay, we treat sine and cosine the same way to find the period if we're just given an equation. Okay, so if I gave you y equals 10x, or y equals sine of 10x, y equals sine of 10x, you would take 2 pi divided by 10, or know that the period is pi over 5 when you reduce that fraction down. It's really kind of what we're looking at there. All right, so let's do another graph here. We're going to graph y equals cosine of 2/3 x over one period. So yes, I'm going to take what? 2 pi divided by 2/3. So when you do that, we end up getting 3 pi. So notice, what's this fraction going to do? A whole number, what, made it happen a lot faster this fraction is going to make the graph stretch and take wider or longer to repeat. Notice now the period is 3 pi. So if we compare that to a normal cosine function, all right, it's longer. We have to find the endpoints still, right? So finding the endpoints, we know 0 and 3 pi are the two endpoints. We have to find the middle points. We got to take 0 plus 3 pi, okay, times a half. That gets us 3 pi over 2. We have to take 0 plus 3 pi times a quarter. Okay, that gets us to 3 pi over 4. And we got to take 0 plus 3 pi times 3/4. That's where the 9 pi over 4 come into play. Then we can plot the points. All right. Now we're able to actually plot these values here, and here's what they look like, on the table. 2/3 x, and then if we use cosine of 2/3 x. The amplitude is still 1. There's no change in what value is in front of the cosine here. So when we plot this, notice we're going to plot it from 0 to 3 pi, and the only thing we're plotting are those points that we just came up with. The left and the right endpoint, the midpoint of that, and then the quarter point and the 3/4 point. That's it. That's all we're doing to evaluate this graph, is we are plotting those particular points when we do this. Okay, so you should be able to look at the table and look at what's going on here. Hopefully figure that piece out. But when we have a fraction in the argument, it stretches the graph out and makes it take longer, okay, for the period to complete. So just guidelines for sketching cosine and sine graphs. The general equation is y equals a sine of bx and y equals a cosine of bx. A represents the amplitude, or how high the wave is going to get. B represents us adjusting the period, okay? The first step when we do this is we always have to find the period, okay? Because the period is important for us to analyze, so we know, the left and the right endpoint, the middle point, the quarter point, and the 3/4 point for us to do our calculations. So that's step 2, dividing it into the equal parts, and then we have to take those parts and substitute them back in so that we know if we are at a maximum, a minimum, or 0 at those particular points that we found in step 2. Okay, so just rehash it. I think we'll be good. Once we do it, we plot all the points, and then we make them and connect all of them, all right, on a curve or a sinusoidal type graph. All right, we've seen enough graphs of sine and cosine. Nice, continuous, smooth curve. I know that's hard, for some of you guys. Most of it, we're just going to be analyzing what's going on here, though. Then, all right, step 5, we're going to draw the graph for additional periods. So I might ask you to graph 2 periods of, sine of 4x instead of 1 period. So you might have to graph it, twice as long. So let's take a look at this piece here, this example. We got graph y equals -2 sine 3x over 1 period. So we have to find the period. So you should be thinking in your head, all right, period is 2 pi over b. My b is 3. So I'm going to get my period first. I know my amplitude's got to be 2. What is that negative going to do to this graph? That's what I want you to ask yourself. I know all this other stuff. What's the negative going to do? All right, so we found the period. The period is 2 pi over b, 2 pi over 3, okay? So we're going to graph it over the interval 0 to 2 pi over 3. Then we got to break that up. We got to find our quarter point and our midpoints. We know our left endpoint 0, our right endpoint's 2 pi over 3. We know if we take 0 plus 2 pi over 3, all right, times a half, we get pi over 3. If we take 0 plus 2 pi over 3 times a quarter, we get 1/6. And if we take 0 plus 2 pi over 3 times 3/4, we get pi over 2. So that's where those values come from. All right, those are our 4 equal parts. We can make a table so that we can analyze everything. All right, and the question marks here, they're kind of showing up. They should be pi's. I don't know why the symbol didn't come through with the PowerPoint correctly, but the little question mark boxes all mean pi. So it should be pi over 6, pi over 3, pi over 2, 2 pi over 3. All right, and then our answers should also have pi over 2, 3 pi over 2, 2 pi. All right, and we're just substituting in those specific values of x. All right, so when I substitute in 0, I get 0. When I substitute in pi over 6, I get pi over 2 as an answer. When I substitute in pi over 3, okay, for x, 3 times pi over 3 is pi. That's why there's just one question mark in there. Okay, and then I have pi over 2 times 3. That gives me 3 pi over 2. And then I have 2 pi over 3 times 3. That gives me 2 pi. And then I evaluate each one of those at sine. I know sine of 0 is 0. I know sine of pi over 2 is 1. I know sine of pi is 0. I know sine of 3 pi over 2 is negative 1. And I know sine of 2 pi is 0. Now I'm ready to do what? Throw in that amplitude in front. So I'm going to take 0 times negative 2, which is 0, negative 2 times 1, which is negative 2, and then so on and so forth. So that's really what this graph is going to look like. All right, when we plug this in, there is one slight error. It should be a positive 2 at pi over 2. So when sine of 3x is negative 1, that should say positive 2 here on the table. So I do have a misprint there on that needs to be fixed, okay? So that's where this value comes from. All right, then we plot the points. All right, so we're going to draw our x or y axis. We're going to plot out the max, min, amplitudes. We're going to plot out the specific points that we calculated. The 0, the pi over 6, the pi over 3, the pi over 2, the 2 pi over 3. Then we're going to make a nice smooth curve that adjoins all of them, and that would be our graph. That is one period of y equals negative 2 sine of 3x. But let's go back to that question. What does the negative do? All right, remember what the graph of your parent function of sine x does. It flipped it. All right, remember sine normally started at 0, went up to 1, and then back down into 0, and then to negative 1, and then back up. This graph goes what? Down, then up. So the negative in front flips the graph, okay? Flips it over the x-axis. So that's what it's going to do. It's going to make everything the opposite when you go through this. All right, and just made a note of that, okay? So what's really going to happen is it does reflect across the x-axis. Okay, let's do another example. We got y equals negative 3 cosine pi x over 1 period. This time, what's your b going to be? Your b is pi. Okay, so that's going to change things up a little bit. The 3 is the amplitude, and then the negative, we're going to flip cosine, all right? So I know that it needs to start below the x-axis here. All right, so 2 pi over pi. So our period is just 2 in this case. All right, this makes it nice and easy to graph because we can divide 2 in half easy, and we know 0 to 2, and we know our quarter points much easier. So we're going to graph it from 0 to 2. Okay, we have to get our intervals. So 0 plus 2 times a half. That gives us our 1. 0 plus 2 times a quarter gives us our 1/2. 0 plus 2 times 3/4 gives us the 3 over 2. And we already have the endpoints of 0 and 2. So those are the points we're going to plot. We're going to fill those in the table. So we're going to analyze, and I'm sorry once again, there's boxes showing up instead of pi. But we're really just going to substitute those values in for x. So 0 times x is 0, 1/2. Okay. I'm sorry, times pi x, because that's what we're substituting into. And then find cosine of pi x. Do you have to do all these steps? If you know what you're doing, no. You can use a table. You can put cosine, you can hit y equals, cosine of pi x in your calculator, and you can look at the table and get the values that way as well. Okay, but this, I'm not going to spend a ton of time on this one because we did it all with sine. We're just doing one with cosine now. So we found all the different values of when cosine's at its maximum, its minimum, and when it crosses the x-axis again as we go through this. Okay, then we're going to plot the points, all right, with our dots, the ones we calculated, and then make a nice smooth connection between them. And now we've graphed y equals negative 3 cosine of pi x. Okay, so not overwhelmingly challenging, but make sure that you pay attention to the steps. Make sure you figure out how we're finding those points that we evaluate using the quarter, the half, and the 3/4 as we go through that. Alright, so just, remember when b is an integer, multiple of pi, the x-intercepts of the graph are going to be rational numbers. Alright, so let's look at another example here. We want to determine the equation now of this graph. So now instead of graphing it, we are looking at this, and I've got to come up with the equation. Alright, the easiest thing for you to pick off is you should be able to look at this waveform and be like, alright, I see the amplitude. So, pause the video, see if you can come up with the equation and get what we get right. But the amplitude of this waveform, our A value, should be what? Should be 2, all right? That's the highest the wave gets, is 2. So from 0 to 2. So the amplitude, the A value, is 2. What's the period in this case? The period is 4 pi. So we got to work backwards. We have to say 4 pi is equal to 2 pi over b, and we got to solve for b. All right, that's going to help us find out what b is. So we have to set all that up and then solve for b. Okay, so this should really kind of help. This is a way of generating the amplitude here, this equation at the bottom, if you didn't understand it. All right, what's really going on is the first two, that's the maximum, minus your minimum, which is -2. So we add those together. 2 minus -2 is a positive 4, and then we find half of that. Okay, 4 divided by 2 is 2. That way we know the amplitude is 2. That's the mathematical way. You should be able to visually take a look at that and see that that's 2. Okay, and then like I was saying before with the period, we know the period, that's how long it completes its cycle, is 4 pi. We set 4 pi equal to 2 pi over b and solve for b. So b is going to be 2 pi over 4 pi, all right, and when that simplifies down, you end up getting a half. The pi's cancel and you have 2 over 4, which is 1/2. So now you found your b. Now we're really, and does it look reflected at all? Yes, because cosine, what's the closest one that looks like a reflected cosine? Okay, because we're starting down below. So to me it's a negative cosine. We know the amplitude, and now we know the argument piece we calculated. All right, since it's flipped. We know if it was a positive cosine, it would have started on the y-axis when y is 2. How do we know it's cosine? Because it's starting on the y-axis. If it was starting at 0, I'm saying it's starting on the y-axis at a value. It's starting at the amplitude. That's how I know that it's a y or a cosine graph. If it was going through 0, it's most likely going to be a sine graph, whether it's going up or down. But if it's going through 0, it's going to be a sine graph. And lastly, real-world application here problem, then we're almost done here. The average temperature in Fahrenheit at Mold Bay, Canada, way up north, can be approximated by this function. F of x equals 34 sine of pi over 6 times x minus 4.3. All right, where x is the month, okay, and x equals 1 is going to correspond to January, 2 is February, 12 is December. All right, all the way up. So we want to observe the graph over a 2-year interval, okay, and see what's going on here. You can put this in your calculator. So if you remember how to do that, you're going to type all that into y equals, then you're going to hit your window button, okay, and then make your x 0 to 25 and your y -45 to +45 when you do this. All right, so that's how you're going to plug it into your calculator and take a look at it. All right, so to find the amplitude of the graph, it's 34. We should know that by looking at the front of the equation. The 34 is in front of the sine graph. Okay, then to do the next part, we have pi over 6. Okay, that's going to get multiplied by the x. That's how we're going to get the period. So we're going to take 2 pi over b. B is pi over 6, and we end up getting 12. So that's our period, which is 12. Should make sense, right? 12 months or 1 year, which agrees with our changing of our seasons as well, right? So according to the model, what's the average temperature during the month of May? Okay, so May is the 5th month, so you can substitute in x equals 5, all right? And when you do that, you will get 12.18, okay, Fahrenheit. Not very warm, right? You got to remember they're very far north, okay? So that's how you do that piece. You're just substituting in 5. For x, you can see it on your calculator there. And if you were struggling to put in the calculator, when you hit y equals, type it in exactly as you see it on the screen up here, and that should help you. And then change the windows like I stated in the previous slide, okay? So next part of this problem is what would be an approximate for the average yearly temperature on base. So we got to figure out what's the average yearly temperature looking at this graph when we do this, okay? It appears the average yearly temperature is what? About 0 Fahrenheit, because that's where the median or the medical line where y equals 0 is. That's the middle temperature for it, okay? Does that make sense? So that one's a fairly easy approximation on this. I didn't mean to jump ahead there, but that's the end of this lecture. So, any questions, email me. Else, see the majority of you guys in class, and we will be moving on to the next one.